All right, well, hello AP Physics students, and welcome to this video lecture that's going to go through how we kind of get these kinematic equations for simple harmonic motion. You took a look yesterday at this thing called the reference circle and how that can help us not only visualize simple harmonic motion through this idea of rotational motion being projected into linear motion, but also how it can help us derive those kinematic equations. So I think the first one that I'd like to go through is how the reference circle helps us come up with displacement. And this is probably the easiest one to see. So again, yesterday, if we have a circle and we just have some point that we called Q, traveling around that circle at some angular velocity, that point Q can be projected down onto this x-axis that bisects or runs right through the middle of that circle. So as Q moves, P is going to be projected down onto that x-axis. So if we want to figure out where P is in reference to the center of that circle, or if we're looking at a mass spring system, if we want to figure out where that mass is in reference to the equilibrium position of the spring, we can just use trigonometry. So you see that we have a triangle here, and the hypotenuse of that triangle is r, but for our purposes, we're going to call that the amplitude. We're going to say that that's the amplitude or the max position that this point P can get, or that the mass on a spring can get. So if we just use trig here, then the x position, okay, so this is going to be our x position. Our x position is just going to equal a, and now it's going to be cosine of theta. Okay, now we can extend this out. If we think back to our previous unit on rotational motion, we said that omega, or angular velocity, was equal to theta divided by time. Now, if I rearrange that for theta, okay, I want to plug something in for theta here, we can say then that theta is equal to omega t, and if we just plug this guy into here, we're going to get our first kinematic equation for harmonic motion, which says that x, the x position of that point P on our reference circle, is going to be equal to a cosine of omega t. Okay, and understand that this directly relates to the motion of a mass on a spring. At any point, if we know what that amplitude is, and if we know what this angular velocity is, and at a certain point in time, we can figure out where that mass is. Now, if we're thinking about a mass spring system, we don't have angular velocity, right? I mean, it's moving linearly, so we don't really have an angular velocity, but we can utilize some ideas that we've already learned in this unit and in a previous unit to help us out with this angular velocity. So if we were just to look at Q doing one full revolution around here, okay, doing one full revolution, well, its angular displacement then is 2 pi, okay? And one full revolution, well, we would say then that that's one oscillation of that point P, or of that mass on a spring. So P would be going from here all the way to here and then to here if Q were to rotate all the way around. So we could rewrite this equation up here as W is equal to 2 pi, and now for T, we're going to put period there, okay? Because remember, period, we're looking at the time of the time it takes for one full cycle or one full oscillation. Now, extending that out even further, we know that T is the inverse of frequency, okay? So really what we can say here is that omega, or angular velocity, is equal to 2 pi times our frequency, okay? And this expression then that we have here can just be plugged in for W, okay? So if I don't give you an angular velocity, if we know what the frequency is, then we could still figure out where that mass is at any point in time. All right, so the next kinematic equation that we can come up with for simple harmonic motion using the reference circle is the velocity of point P, or of a mass on a spring at any point in time. So I drew a similar triangle up here to represent, or to go along with, this triangle that we have down here. Now you can see that the velocity of P right here is pointing inward because it's going to be moving this way towards the equilibrium position, or the center of the circle in this case. And that velocity of P matches this Vx up here. Now where is that Vx coming from? Well, if we think back to our unit on rotational motion and circular motion early in the year, if Q is rotating around this circle, at any point it has some amount of tangential velocity. So we can take tangential velocity to be the hypotenuse of this similar triangle here, and we can say then that Vx is going to be equal to Vt times the sine of theta. Now, we can relate tangential velocity to angular velocity because we know that tangential velocity is equal to r theta, or r omega, which is our angular velocity. Now, we don't want to use r, but we do know that r is equal to the amplitude. Okay, so I'm actually going to write in here tangential velocity is equal to a times omega. Okay, and now that can be plugged in to this equation up here, where we can say that Vx, and I'm just going to write V now, V is equal to AW times the sine of theta. Now, there's a few things that we need to keep in mind here. At this position, okay, if P is right here, notice the direction that V is pointing. V is actually pointing to the left, okay? So we actually need a negative sign here, okay? We need a negative sign in front of our amplitude, in front of that whole expression, really. And also, just like we did on the previous slide, we can replace this theta with omega t. So I'm going to rewrite this. I'm going to say V is equal to negative amplitude times omega times sine of omega t. And then just remember that omega is equal to 2 pi times our frequency. Okay, so really with this reference circle, we're just using a lot of trig to develop these major kinematic equations. All right, one final slide, which is going to help us derive acceleration. All right, finally, for acceleration. Again, referencing back to previous units, if we have an object that's traveling in this circular fashion, okay, yes, it has tangential velocity, but what's keeping it moving on that circular path is centripetal acceleration, which is always directed towards the center of that object, okay? So what we can say here then is that acceleration, and this is the acceleration of P now, is just going to be equal to centripetal acceleration times the cosine of our angle theta in this reference circle. Okay, so we're going to have cosine of theta. Now, again, this acceleration at P is pointing in the negative direction, so we need to have a negative sign here. And now, once again, we have an expression that relates centripetal acceleration to tangential velocity. So we can say that AC is equal to VT squared divided by R, okay? Now, once again, I don't want R there, but we know that R is equal to our amplitude, so I'm going to have VT squared divided by amplitude. And once again, I know that VT is equal to omega times radius, or times our amplitude, so I'm going to plug that in here. AC is then equal to omega A, and that's all squared, divided by A. So my expression for centripetal acceleration here is going to be omega squared A. All right, and now plugging that into this guy up here, I'm going to get A is equal to negative omega squared times amplitude times the cosine, and instead of putting theta in there, I'm just going to put in our omega t. So there's the derivations of all of our kinematic equations using the reference circle. The final slide is going to show how these all can be useful for us in terms of simple harmonic motion, specifically with masses on a spring. All right, so this final slide, I just want to relate the reference circle to simple harmonic motion, because I think it's a little bit confusing when we're trying to say that we can relate rotational motion to linear motion. But again, let's say that Q starts here. Well, then P is just going to be projected at this point right here. And that would represent for us when that, if we're thinking about a mass spring system, that would represent when our spring is fully extended. So it's at max amplitude, okay? And that would be positive amplitude. So this is representing A max, or amplitude maximum, okay? Now, as Q begins to rotate about, okay, it's going to rotate about, P is constantly going to be projected onto this x-axis until finally, when Q is up here, P is going to be right at the center of this circle, okay? When P is right at the center of this circle, we can imagine that that represents when our mass spring system is at equilibrium, okay? So this spring is at its relaxed or equilibrium position, okay? So this represents equilibrium. Okay. Now, Q continues to rotate. Q continues to rotate, and then it gets to this point over here, so P is going to be projected over here. We can represent that with our mass spring system as when that spring is fully compressed. So that would be our negative amplitude max. So everything that's been said so far is just dealing with the displacement of P, and therefore the displacement of this mass attached to the spring. Now, what about velocity and acceleration? Well, let's say that let's say that P is at this position, okay, because Q is at this position. Okay, that would mean that our block is fully extended out, so our spring is fully stretched. Now, because that spring is fully stretched, for a moment in time, then V is 0. Okay, so when that spring is fully stretched, that spring is not moving, or that mass is not moving at that point in time. But what that means is if our spring is fully stretched, the restoring force, or the force within that spring, is at a maximum, because this spring wants to go back this way to its equilibrium position. Now, thinking back to Newton's second law, if force is maximum here, well, then the acceleration is also a maximum here. So acceleration is also going to be a maximum. at that fully stretched position. Now, the thing that we got to keep in mind is that if force is pointing this way to the left, then that acceleration is actually negative as well. Okay, now moving on, again, as Q rotates to this position here, P is going to be right at the center of that circle. We're going to be at equilibrium for our spring. So when that occurs, force is a minimum. Okay, force is non-existent there because that spring wants to be there. So what that means then is that velocity is going to be a maximum. Velocity is going to be a maximum, but again, if there's no force there, then acceleration is equal to 0. Okay, and now again, Q rotates, P is projected to here. That's going to represent our fully compressed position. And really, our fully compressed position is just a mirror of our fully extended position. So again, for that moment in time, velocity is going to be 0. Our force is going to be at a maximum, but it's actually going to be directed to the right because it wants to push that block back to the equilibrium position. So our acceleration there is also going to be a maximum. But notice again that if the force is pointing to the right, then our acceleration has to point to the right, so it's going to be positive as well. Okay, so in this video lecture, we derive those kinematic equations. I tried my best to relate the reference circle to simple harmonic motion here, specifically simple harmonic motion with masses on springs. So we're going to utilize this in the coming days, and we're also going to throw in the reference circle and simple harmonic motion with pendulums. So take care, AP Physics students.